computer.
Cool. Thanks, chat, for letting me know you can hear me. Monitoring that per usual. I can hear someone typing. Sakanya, that's okay. Yeah, so some logistics right off the bat. Sorry for the small text. I'm going to write bigger today. That's the game plan, at least. So homework 1 grade should be on Canvas for everyone. If you don't have a grade, it means you didn't turn it in, or no, it means you didn't turn it in. So please figure that out. Email us if it was just an oversight. That's one thing. And we can probably let it slide this once. In the future, late homework won't really be allowed. So please get that in at least before we grade. You know, you'll take a late penalty, but if it's after we grade, there won't be so much leniency, barring any kind of special circumstances. If you want feedback on those grades, please reach out to Sakanya. She graded most everything. I'll be grading about 3 or 4 assignments. It'll usually probably be the same 4 people. I'll actually probably let you know if I'm the one grading your stuff, so you can just come to me for feedback. That's fine for those 4 or 5 people. I do some grading just to keep touch where people are missing problems, where I could improve, that kind of stuff. Yeah, so for feedback, see her. If you see her, she tells you you got something wrong you don't think you should have gotten wrong, or you want points corrected, then reach out to me, but meet with her first, okay? If you haven't met with her and you want to dispute a grade, then I won't entertain it. You need to meet with her first, talk over the grade in office hours, before meeting with me and wanting points back. Probably won't ever get points back. These are pretty cut and dry grades, but there is a chance that we got something wrong, or weren't consistent with the grading. That's fine. You know, we'll correct that as need be. You guys probably notice a lot of the grading is kind of all or nothing in this class. Unfortunately, with functions, you kind of get it or you don't. We don't give a whole lot of partial credit. On this first assignment, we did give a little bit for correct type signatures, but incorrect definitions. That won't always be the case. In the future, there won't be as many type signature stuff to give partial credit for. So it just won't be there. So please be cognizant of that. The rubric will change homework to homework. That probably won't be put out before it's due. It might be, I'm not sure yet. Sometimes the rubric doesn't present itself until we're actually looking at solutions. Also expect solutions out at some point. I need to do that for the CA anyway, so there will be a solution notebook put out sometime in the next couple days. Yeah, so Pseudo asked, can we use helper functions? Are there any similar guidelines? So I am going to put out some guidelines for doing the programming homework. It's an old write-up. It basically says only use the stuff we've defined in class. All of that is fair game. Don't go to the standard library in Scala. Most of it won't work because we've kind of redefined stuff and the definitions aren't necessarily the same. So be very cognizant of that. Don't go reaching out to the Scala standard library. We'll give you a standard library to work with for each homework. And yeah, and Pseudo, I was going to address that because I thought that's what you were asking. So he said, oh, I mean making your own helper function. That's perfectly allowed. If you want to make helper functions, go ahead. Now be careful with that because there's a way you can start writing helper functions in such a way that it's cumbersome and kind of it's more than you need. If it's like egregious and you're defining a different function for every case, that might be a problem. But that's something I'd probably reach out to you guys on, and we have a little discussion. It's like, here's how to write this the right kind of clean, the right way. But yeah, definitely helper functions are fair game. Feel free to write helpers. In some cases, you have to. So yeah, when in doubt, ask though. That's what Piazza is for. So if you're like, I feel like I don't need 4 helper functions for this assignment or something, like ask. That's fine. Homework 2 is up on Canvas. Like I said, we will distribute a standard library with each of those. Please open those and see what's in there. They're not very big, but there are functions we've kind of defined in class. There might be 1 or 2 I've thrown in there, like I think the less than or equal to function we didn't actually write. So take a look at that. That's kind of what's in your palette, your sandbox to use for solving programming assignments. So going forward, those are going to be really, really useful. And on occasion, we might goof it up. So tell us if there's a function that should be there that isn't. In most cases, we keep it up to date. The current one for homework 2 is good, though. I went over that yesterday. You will need to make sure, and this is really important, that that standard library file
Hello, we can't hear you. Come back to us.
Please come back.
Hello.
It's gonna be okay. Just give it a bit.
Oh, this is weird.
No, I'm saying if this one takes like 10 gigabytes from this one here, it's like just enough to do. It takes like 2 hours to, yeah, it's like the very end.
Better, guys? Can you hear me?
Yeah.
Perfect. Thanks for bearing with me there. That was a weird set of problems. It won't let me rejoin. Okay, so where was I when I cut out for those online?
Last thing I heard was, and one thing that we'll do for you that's really important is, or something like that.
Ooh, okay. So yeah, so I think what I think I was saying was make sure you have the standard library in the same folder as your notebook for the homeworks. Otherwise, you'll have problems compiling everything. As for those using coding.ccell.io, that's another resource you guys can use. If your VM isn't working, or if you just prefer it, that's fine, but just note it's not necessarily super reliable, so try to use the VM, it's more consistent. And if there are problems for those of you using coding.ccell.io with getting the standard library to work, please let us know earlier in the week so we can try and fix that. That's going to be really, really important, so we have time to fix things if need be. Otherwise, on my list, today's quiz is up, so you guys, it should be open now. Some folks in class accidentally took it already. Yeah, but you won't probably be able to answer those questions till after class, so hold on for that. Someone asked when my weekly office hours will be regularly held. Let's say, what's today, Tuesday? Tomorrow's Wednesday. Let's say Wednesday before class, and I'll post those tonight for sure, a time. And it'll be just on Zoom for those of you that are attending in person. Feel free to come to campus. I'll be somewhere around here. So, yeah, so pseudo, yeah, so for those of you that already took the quiz, I'll email me and I'll reopen it for just those that already took it. That's kind of okay. Yeah, so no quizzes on recitation days. I was going to originally, but I think the homeworks kind of serve that purpose anyway. So not necessary really to have a quiz. We're not usually presenting anything super, super new. So I don't think there's any sense in having a quiz on those days. Yeah, so pseudo, shoot me an email and I can open that back up for you. There are a couple other people in that situation. So any other logistic type questions before we jump into today's material? Yeah, Maddie. Ooh, that's a really good question. Yeah, plan on the midterm being next week. Probably I'll open it Friday and you'll have 24 hours kind of deal. I don't necessarily want to do it on a day we have class. Go over the notes and you'll be good. It'll be stuff we've gone over for the most part. There might be one essay type question that's more programmy-ish. Oh, sorry, Linnea, probably next Friday. This is the game plan. So not this Friday, next Friday. Yes. Mostly multiple choice, almost entirely multiple choice. Maybe one or one kind of conceptual type question that you will have to do some writing for. I'm not sure exactly what that'll look like yet because I haven't written the midterm yet. So yeah, just hang in there on that point. More info on the midterm next week. Plan on it being Friday of next week though. Mostly, I don't really want to write it this week. I don't think you guys want to take it this week either. That gives us a full week to kind of do maybe the odd review question and stuff like that. So. Any other? Oh, Linnea, good question. So Linnea asks, will it be the exam be programming Scala like the homework or defining functions like we do in class? It'll probably be a mix of the two to some degree. Most of the kind of like, what is this type questions will be in the mathy notation we use in class. It's just a little bit more concise. But I think the idea on the exam is you should be able to read both fairly proficiently. And if that is, not the case, then kind of study up kind of deal. I think 2 weeks from today, class-wise, plenty of time to study. So, and of course, office hours are there handily for that purpose. I'll probably have Kathleen do some kind of review session next week. So be on the lookout for that. Probably it'll end up being before class because class already goes pretty late. So yeah, be on the lookout for that. And as far as other resources goes, Post and Piazza, I'm happy to provide that stuff. There is some writing and more kind of spelled out reading material that we'll be posting this week. I have to migrate it all over from another service. So it's been taking a little longer than I wanted it to. But be on lookout. That should be tomorrow morning's kind of task for me to do. So be on lookout. Any other questions? I've got to look at the chat, make sure I didn't miss anything. But I think we are all good. If I do cut out again, please say something pretty quick. You guys were pretty on top of it last time. The laptop shouldn't go out. It's the iPad that's a little finicky sometimes with Wi-Fi. Sweet, so let's jump into it. Now that I'm like super winded, I was talking too fast there. So today and this week, we're going to be transitioning partway through the week from functional programming into the study of programming languages formally. It does build on the functional programming we've been doing, so it's not really a big departure. But today and tomorrow, we'll be kind of finishing up our discussion of functional programming. We'll pick it up probably once a week. We'll have a little bit of a lecture on that, but otherwise it'll be more kind of hardline PL topics from here on out. Today, we have another pattern that I'd like us to look at. That was too much. And here's that pattern. So here are a couple of functions. We have sum, which we're really used to now, and prod. Prod is like sum. It's taking the product of a bunch of numbers in a list. And sum takes the sum of a bunch of numbers in a list. So two fairly familiar kind of ideas from mathematics that most of us have kind of seen in the past. Is there a pattern here? Is there a commonality between these two functions? If so, what is it? And can we abstract that? Take a second to think about it. You'll also notice one of these might be a homework problem, so it's probably in your benefit to write it down. I realized that after writing it down in the notebook today. So free points for you guys if you can write that down quickly. So whoever dash is, I will get to that question let's do that at the end of class. Remind me to answer it though. So he asked what's the 30,000 foot view conceptually of what we've learned so far. Happy to answer that. Let's just save it till the end, and I'll be able to tie it all together a little bit better then. Okay, so now the question we're thinking about, what is the commonality between these two functions? Can we pick it out? What is it? Or maybe you could also answer the same question, what's different? Those are kind of the same question in a certain sense. Yeah, Maddie.
I might just be wrong, but it looks like in the sun.
Yeah, and otherwise they're pretty similar, right? But not quite the same otherwise, but that's one point. So here we have the addition operator there in sum, and we have multiplication in product, right? So that's a difference, right? Otherwise, if we look at the cons line, it takes the element of the list in each case, does some operation to it on the recursive call of the rest of the list, right? Okay, what else is the same or different here? So we just looked at the cons case, right? So those are the similarities, differences there. What about for the nil case?
0 and sum.
Yeah. So 0 for sum, 1 in prod. Those are different, but is there, in a sense, are they the same? They are both constants, but there's actually a special name for this kind of constant. Does anyone know, any math people maybe know that if we have any math major? I didn't ask, is anyone a math major in the class? If you are, you should know what this is called.
Is it the identity element?
Yeah, so there's an identity element, or you would, mathematicians call this the identity of the group, which basically says, you know, when you add this thing or in multiplication for product, when you multiply against this thing, the result is unchanged. Okay, and this sits at the core of kind of what we're trying to abstract here. So there's an identity element, right? So actually, I'll write that down. Okay, so we have some identities, we have some different operations. Can anyone abstractly tell me what's going on here though? Like what is the core similarity between these two things? And it's gonna sound kind of abstract. It's not supposed to be super specific. Yeah.
They both recursively call their own function to end up at one value.
Yeah. So they kind of recur on the list in order to produce some kind of value, right? So yeah, let's write that down. Oh, you already did the quiz, so you knew the answer to this problem. So recur on a list to produce some composite result. Right, so kind of taking the sum of the parts, right? Right, and some kind of more literary language, right? Yeah, so pseudo is getting a little ahead, which I like to see because not really ahead, one step ahead. So pseudo says we can probably turn this into a function similar to map, right? One that can be used for other functions. So we can write a higher order function here, right on pseudo. And we can abstract this into a single function that maybe captures that commonality, okay? Also want to note the types are the same here, which is kind of a good clue that there might be a potential. Sometimes the types will betray, this is a candidate for a pattern, or things of this type might sometimes have a similar pattern, not always, but in this case they do. Because I could just as easily write list of n to n, that be like the first element of the list, right? In which case it would have the same type, different behavior though. Which actually, come to think of it, you could write in this style. Anyway, let's try and abstract this. First, and pseudo says, oh, this is fold, isn't it? Because pseudo also already took the quiz. So this is gonna be what we call a fold, right? So we're folding a list into a single, not a single operation, into a single value. Okay, Maddie, can you read this better? Is this a better size?
Yeah.
Okay, perfect. You're not lying, right? Okay, cool. Perfect. So hopefully everyone online can read the size of my text okay. If not, say something. That was a critique today. So just want to make sure I'm writing large enough for everyone to see. So in comes the fold function or the fold operation. We're going to start by writing kind of an intermediate version of fold. Okay, we're not going to get straight to the final version. But let's write, how can we abstract these two functions here? What is the common? Let's try and abstract both of these first. What should the type be here? Yeah, so that should definitely be present, right? So we'll call this fold nat for now, or nat list. Fold nat list. It's a little wordy, but that's okay. Or actually, we can just call it fold nat. That's fine. You can see the idea across. And it should definitely be a list of nat to nat, at least getting started with the abstraction. Okay, should there be anything else here? I left a gap, so the answer is, of course, yes. But what else do we need to provide this?
You need the variable that represents which function you're using.
Oh, can you say that a little louder? You're coming out kind of warbled.
Sorry, I said you need a variable that represents the function you're using.
Yeah, so a variable that represents the function we're using, right? So what is the type of that function? So pseudo says A to B. Does that work here though? Not really. A to B doesn't really work here because we're not dealing with variables, type variables yet. We're just dealing with naturals for now. So let's get rid of that. But you're on the right track. So just keep it in the language of naturals, right? What's our combining operation here, right? So look at plus and multiply. What's their type? N to N? Try again, almost. And pseudo, you're almost there. Kath, not quite. No lists yet. What's multiply and plus? What's the type of multiply and plus? You're almost there. It's N to N to N, right? It takes two arguments, right? So here we have an N to N, and I've again not given my spells enough space, to N, right? So it takes two natural numbers and produces a natural number. Multiply, addition, they both fit this mold. Minus also does. Powers do as well. So if you're like taking something to the power of something else, same there. Chat, awesome for putting out a bunch of responses. Keep that work up. I like it. Do we need anything else? Is there any other variability between the two? So one of them's the operation. Where else did these two functions vary? Yeah, the identity is different between the two, right? So should we provide that as an argument maybe too? Well, yeah, it varies between the two functions. So let's provide it as a variable, right? So, and that will also be a natural number here, okay? Sweet. So now we have a type. That's a good start. And this is why, actually, this is a really good case where starting with just giving the thing a name and a type is actually more than just a trivial task. Sometimes it takes some working out and you want to abstract something. And laying this out piece by piece actually is super helpful. So hopefully this justifies the madness in the method a little bit. Cool. So let's try and define the functions. We've got fold nat. Okay, fold nat's going to take some f, an operation. It'll take some identity number, right? We'll call it ID. Don't confuse this with the ID function we wrote. Different ID. Actually, I'll just call it I for our purposes. So we have I, some identity. And then we take a list, x's, right? Can we do anything with x's on its own here? Or do we need a pattern match? Can we write the output? Do we need to introduce something?
Got to make sure X isn't just nil.
Right, so we could do nil or cons here. So a pretty typical case split again that we're hopefully getting very used to by now. So we got two cases, one for nil and one for cons. So we'll put nil here, and then we'll put cons x's. Okay, I'm going to start lining up our equal signs more. It's just easy. It's not easier to read necessarily. It's just nicer. White space doesn't matter a whole lot if you guys haven't picked up on that, which is really nice in these languages. So, yes, Niket, that's an I after F. The identity here. Yeah, so that 0 or that 1, the starting value. Right, so that's another way to look at this I. It's a starting value. It'll make more sense in a second why we call that a starting value. And I'll tie that into something else we talked about last week as well. So Okay, so what do we want for our nil case? Again, use sum and product as kind of a schematic here. What do we want as an output for nil? Yeah, so it's gonna be I. Why is it I? Yeah, and that's the output for the two functions above, right? It's just the identity. We've created a nice handy variable for it. We can put it there, right? Now, how about our cons case? What should we do for cons? This one's a little bit more interesting, of course.
Started with f of x.
Okay, so f of x. Okay, and f should take one more argument here. And I believe that should be a natural number, right?
So that's what the first call.
Speak up.
Probably where it's probably where the recursive.
That's where the recursive call should go, right? If you guys are in the room, speak up so everyone else can hear you too. Maddie, I'm looking at you. Okay, so we can put the recursive call here. I just banged my arm really hard on the desk. That hurt. 1, 0. So the recursive call here, I'll put big parentheses. Recursive call would be calling fold nat again. Okay, and what do we need to give to fold nat as arguments? So it takes quite a few arguments, as we can see by the type that we wrote. What all should it take? Oh. Someone online about to go? We'll give Conlon a break.
Yeah, I was about to say maybe the F comes next.
So the F definitely comes next, right on. What about the next value? It's got to be the I. Okay. And X's. Okay, I think I like what we see. Is there another way we could have written this? Could we use an accumulator here? How could we?
I think you can.
Okay.
Just because it's multiplying something every time. So like the first time it'll multiply by 1. And then,
Yeah, but what does the output look like? What could we write here?
well, I guess we'd have to call a multiply still.
You do somewhere, right?
Okay.
But we could make this tail recursive, right? How might we do that? So I'll give this one to you guys. So making this in a tail recursive style, which is usually how you see this written, you could write fold nat of F again, that's fine. But then here where we have I, we instead do F of IX. And then give it X's. Do I need to explain why those are the same thing?
Yeah, would you?
Yeah, so let's do this actually with, should we evaluate it? Yeah, why not, right? Let's evaluate it and see it concretely. So let's first do the first definition and see what that looks like. So let's just do fold nat. We'll basically recreate the sum function. So fold nat with plus the starting I here, because plus will be 0. Okay, and let's do the list 1, 2, 3. Okay. This is equal to, okay, we look at f of x, which is going to be plus x, the first x is 1, and then fold that plus 0, 2, 3. Okay, now let's try and evaluate that inner one. So you get plus 1, and then this inner fold nat will give us plus 2, and fold nat plus 0 and 3. I'm going to make this shorter on us, so remove the 3 from this example. Make our lives a little easier. So that'll just be the empty list, right? Now, fold plus 0 empty list, we have nil, right? That gives us I back. I here is 0. So now we have, I'll change our notation, 1 plus 2 plus 0, which is equal to 3, okay? That's a solution. Now let's do the same, but using the other definition. So we have, again, fold nat plus 0, 1 and 2. This is equal to, let me scroll a little bit. Okay, so now if we look at the definition, it says, okay, well, it's another call to fold nat. I give it plus again. And then now I need to change the accumulator, that I, that identity thing is what's changing now at each step. So it's no longer really the identity. It's really capturing what an accumulator is, if you think about it, right? So it's kind of a little bit changing what that variable means. In effect, when you call the function, it'll be the same, but it's changing it what it means at each step now. So now I do f of ix, so that's plus I here, which is 0, and x is 1 here. And then we do the rest of the list, which is just 2. Now, the convenient part about this is we can already evaluate that to be just 1. So cleaner execution here, much cleaner. So now I take this and fold nat plus 1 in the list with 2 inside it. Okay, so that'll be fold nat plus, and then here it's 1 plus 2 this time, so we'll get 3. And the empty list here, which then results in 3. So same result, just 2 different ways of evaluating it. One's tail recursive, the other isn't. I prefer the tail recursive definition. It's a little cleaner. It's not necessarily as intuitive, but it gets the job done, right? Does that make it a little bit more clear why they're the same? We could also write a formal proof as to why that is. We're not going to do that, but we could. They are the same function. So, any questions so far about fold nat? Cool. So, anything to talk about here?
So you're saying the second definition in yellow at the bottom? Those are back up at the top. I'm sorry, the one in yellow. So where you have fold nat f on fix xs, that's tail recursive.
Yeah. So this one is the tail recursive one.
Okay.
Yeah, and therefore it's a little cleaner, a little faster. We prefer it. It won't give you stack overflows. Please write it like this. If you write it the other way, it could cause problems later on, right? Because you maybe hit a stack overflow. You don't want that. That's bad time. So, I'm sensing a question.
Yeah. Is the first F technically the accumulator? in that?
Say that again.
Is your first function caller, the first F, is that technically the accumulator?
This part?
Yeah.
No, that's me just passing the function back in so it can use it later.
So X is
This thing is the accumulator here. Yeah,
I see.
yeah, that guy.
So that one's calling a function.
Yeah, it's calling the function, it's building up a value that eventually will output.
I see.
Does anyone notice a similarity between this and a construct you might use in imperative programming? It's like your best friend in imperative programming. What's everybody's favorite kind of loop? Yeah, a lot of people are saying for loop. Whoever said do while, you're just silly. It's a for loop. Everyone's favorite's a for loop, right? It's the coolest of the loops. Folds are kind of like for loops, right? So if we think about it, we have a looping piece here, and then at the end, we end up with some result I. So if you think about for loops, usually kind of like piece through an array or a list and make something new out of that list, right? And sometimes it's changing each element. That's fine. Like a new list is a composite value, right? In some sense, not based off this definition. This doesn't work for that. But like, if I wanted to write the sum function of an array and say C, it would have a similar type if you tried to give it a type, right? It would, like, I give you an array or a list and you get a number out, right? And that operation could be picked out and abstracted. The identity element could be picked out and abstracted. Yeah, so great. A lot of people prefer do while. That's an interesting, I would call that a hot take. But I don't know, preferences are preferences. I'm sure you guys have good reasons. It definitely is more aesthetic, I'll give you that. I am a fan of do while, but for loops are way better, in my opinion. I mean, I don't know anything, but literally, I'm not an imperative programmer. I really don't like that stuff. So let's go with this tail recursive definition. I've kind of copied it back down here so we can continue the discussion a little bit. So this is all fine and well, right? But what if, for instance, let me think of a good example. What if I didn't want a number to be my composite value? What if instead I wanted to create a string out of all the numbers in the list? So I wanted the output to be a string instead. Oh, and just to keep the do while thing going, Pseudo says, I've never actually used a do while loop in my 8 years of programming, which is a throwdown if I've ever heard one. So there will be some fights on Piazza, I guess, later today. We can start that debate. Okay, back to the question. What if I wanted to output a string? So like, could this be a string?
My guess is it has to have the same type as the accumulator.
Ooh, really good point. So Conlin's guess is that it has to have the same type as the accumulator. I think that's, yeah, that's for sure gonna have to happen. Why do you say that though?
If you're, I mean, the same way we just wrote the with the tail recursive one, you wouldn't be able to iterate through anything if you added a string to a natural number.
Right, you couldn't add a string to a natural number necessarily. So for sure, like an I is the output, right? At the end of the day, no matter every execution of fold nat here is going to produce some I, right? And that I better be, you know, that accumulated value better be of the right output type, right? So let's try and abstract that out. How could I abstract this? Well, we need to change the type of the function. So, pseudo, we'll get to that question in a second. Pseudo says he doesn't know if we can put a string function in the first argument. I'd argue we can, but we'll get to why in a second. So let's change this. We'll still call it foldnat for now. We'll get back to that in a second. So we'll still call it foldnat. We'll call it foldnat prime. What should the type of this be? So I'm going to copy the old one, and we can alter it where we think we need to alter it. So what needs to change here for sure? If we want our output to be different, what should change? Like definitely the output type, right? So the output type at least should be say a string, but that's getting kind of redundant. So what could I put there instead? I don't want to write a different fold for every possible output. What could I put there? B, right? Like just some variable, a type variable. So let's just put B here. And we can specialize it to strings later. What else needs to change?
Your function's probably going to have to become one of those A to B's now.
Ooh, the function might need to be an A to B something. So how should we change that? So if we look at the function, what ought to change?
The accumulator needing to be the same as B. We would also say that like the starting value for that function would need to be B.
Okay, the middle value ought to be a B.
Yeah, and then since we're going to be accumulating with that, it also has to end up being a B.
Okay, and then the output ought to be a B, right? Because that's going to be the identity or the output, right? Cool. Do we need to change anything else? Or is it good as it stands? Tell you this isn't quite enough yet. Yeah. Yeah, that identity term might not be a natural number anymore. It actually won't be, right? It has to be a B as well. So we'll also change this part to B. Cool. So this is our new function. Will the definition change at all? No? I'm seeing a lot of shaking of heads. The definition will stay the same. It won't change at all. And when trying to abstract types like this, it's usually a pretty good sign if the definition doesn't change. If all I'm doing is kind of plugging in variables here, which is all I've done, I haven't changed anything on the input side. The inputs are all the same. The definition should probably be the same, right, if I'm trying to abstract. Okay, so can we write this toString function, assuming we have some way of converting to strings? Well, sure, now this is just gonna be, you know, we could call this function, say, list toString, and it takes a list of nat and goes to string, right? And we could define this as, you know, x's equals, and it's going to be like a fold nat prime. And what do we give it? What are the arguments to this function? So let's say we have an append function, right, for lists. Strings are just lists, so we could put append here. We need some identity value. What's the identity value for lists? Well, probably the empty string or the empty list, right? Same thing. And then we give it x's. Okay, so we've just specialized this a little bit more. And that would produce a nice appended string, as we would expect. Now my question for you guys is, does this have to be a list of numbers? Could I do this with other things? What if I wanted to, say, fold a list of strings into a single string? It's essentially what I'm doing here, right? How might I abstract foldNat prime to work on lists of other things? Yeah, so first, I'm gonna write this question down. So can we abstract further to be any kind of list? And of course we can. So yeah, Aaron says rightly, we can change this to be B's, right? But maybe not B. Let's actually say A here. Okay. And pseudos come in with the definition. In chat, and I'll rewrite it here. So now we'll call this new function fold. And this is going to be our final definition of fold. So please write this one down. Fold has a type. That type takes a function from A to B to B. It then takes that starting value or that identity. It won't always necessarily be an identity, but it'll take some starting value. That starting value will be of type B. And then it will take a list of A and produce a B. Look good? Cool. The definition is just the same definition that we had up here. So I'll copy that down for us. So we managed to do pretty good here. We just kind of changed the types at the end there. Of course, we'll need to change the recursive call to fold as well. Any questions? Everyone follow that at least decently well? Cool. I see a lot of writing in class. I'm assuming people online are still kind of writing, processing stuff. Fold is a really special kind of function. It captures a lot of different stuff. And actually every function I believe that we've written on lists could be written as a fold, I think. All but maybe one or two, including map. Map is actually a really special kind of fold where you output a list, right? And so here I can actually write map in terms of fold. I don't think this is on the homework. If it is, I'm being really nice to you guys this week. So map in terms of fold. And I could write this as, give map a type, per usual. So we take an A to B as an argument. We take a list of A and get back a list of B, right? Hopefully there are no qualms about that definition. And we could say map F X's is equal to fold. Okay, let's leave the function part blank for now. We'll get back to that. What's our starting value for map gonna be? If I'm producing a list,
List A that you input.
is it the list A? No, because then I'd get, my output would just be, it'd end up just being the identity type, right? You wouldn't actually do anything to the list. Could it be the empty list? It's going to be the empty list. So our kind of finishing value, or you can look, what does, if I give you an empty list, what does that map to for map? Maps to the empty list, right? That's the other question you ask for figuring out that identity element. It's not always an identity. This is why I say that, because it's strictly speaking, in this case, it's not really an identity. Yeah, so we can write here empty list or nil. And then I need to give it a list, X's. Okay, so now what goes in that hole? What's the function we need to give it? Well, at each step, and let's specialize this actually while we're at it. So there's a hole here. And what's the type of this hole? A to B to B. Oh, and I guess fold should, oh yeah, no, never mind. I'm not getting ahead of myself. If we specialize this, so A to B to B, here A, we can look up, okay, well, A is going to be whatever our list of something is, right? So our list of something here is this X's. That X's has type list of A. So it takes a list of A, or sorry, an A, and then it also takes, well, what's B here? What's our output type for the whole thing? Takes a list of B, and then outputs a list of B. Okay, so it's kind of a little congested there. That's just a hole, right? So how do we fill that hole? Okay, so we can do this by, I'll erase this. I'll see if I can fill this all right there. So we'll take in the A. I'm going to actually introduce some new notation here. So this lambda, I'll explain exactly what it's doing in a second. We use this lambda whenever we need a variable, we have a function, and we need to actually kind of pull the variable out. We don't want to give it like a named function yet. We just want to create a function inline. Inline function, anonymous function, lambda abstraction. Those are all the same term. These are called lambda abstractions. Yeah, lambda. So you can do lambda x here, and x, and you put a period after it. That's just what you do. Lambda x, and then at each step, we're going to do cons, and I will need more space. Cons of f of x and then this function takes two arguments. Actually, I apologize for those of you writing in pen. Move some stuff around real quick. Cons of f of x, and I'm also going to have lambda x and lambda x's, which is the list so far that we've computed. That's that B part in the A to B to B. That's the B you're getting as input to that function. cons f of x, and then here we will put x's. And it'll do this for each step. I believe I've written that properly. There's a chance I wrote that wrong. But this gives the idea, at least, that you can write these things in terms of each other. So fold can be, or map can be written in terms of fold, not the other way around, but you can write it in terms of the other. Yes?
What is lambda?
Yeah, so let's talk about what Lambda is actually doing. So this is the other topic for today. Lambda abstractions. Lambda extractions are useful when you have a higher order function and you want to apply it, and you need a function there, but you need to do some stuff with the arguments. So you don't want to just say, if I'm calling map, I have a hole here that's of type A to B. Okay, and say there's an X's there, right? That's a call to map that we would expect to see. But let's say there, let me try and fix that. Great, perfect. I need a function there, but I haven't defined it. I would need to write a helper function, say. Instead of writing a helper function, let's say I want to write a helper function that takes the argument. And you could match on it, but we won't here. And does some complicated set of operations to it, or maybe you need the X twice. So for instance, map, and I have a helper function here called F that I want to give to map. And let's say F of X is equal to X plus X plus, or yeah, actually just X plus X works here, right? So it kind of doubles everything in the list. How do I write this using that? Like I can't just give it plus, right? So I couldn't, for instance, fill this out with plus X, doesn't work, right? Why doesn't that work? Well, I don't have this X in scope. Okay, so this definition is no good. Instead, what I can do is I can write map of lambda X, which brings the variable into scope. And so think about that as just being another function I'm defining. I'm saying this is a function, X is the input to it. And then my output is plus X and X. And then you give it X's as well. Okay, that's how you would write that doubling function, because I needed two X's, right? I couldn't just say plus, like plus 5. Like that works all on its own. I kind of needed, well, I needed to use it twice, right? And so because I needed to use it twice, I had to write this lambda abstraction. And by using this lambda abstraction, it brings in these variables in the scope that I can then use inside the function. I could write a helper function that does it kind of like I did here with F. This is the same as F. So here, I'll write that down. F is equal to lambda X, X plus X, right? Those are the same thing. They're equal, not definition. I'm not like proclaiming them to be equal. They're equal because they're equal. They're the same thing. They compute the same elements, right? It's just another way of writing functions that we'll see with higher order functions. It becomes really useful. There will be some practice with it on next week's homework. So don't worry if it doesn't make quite a whole lot of sense now, that's okay. But know it's used to create a function where you don't need to like write the type, write and give it a name. Say it's a one-off function. I won't ever use it again outside of the map or outside of a fold. I can just use this lambda abstraction instead. Cool. Yes, Maddie.
Would you be able to show kind of what that would look like in code? I'm not really following it. Like just to clarify.
In like Scala,
Yeah, just you don't have to like write it.
it'll
Kind of-
wait till Monday.
okay.
Yeah, we'll introduce that syntax on Monday. It'll make more sense. It'll be very similar syntax. but yeah, so, and I mean, maybe the code examples right here is it would actually look just like that, but in Scala syntax. So bear with me on that. I promise we'll get back to that. The thing about lambda abstractions is trying to teach them in class. It's a little confusing if we don't start from the lambda calculus, which you guys have probably heard about. We don't take that approach in this class. So it's kind of weird. We have to work backwards and show you why it's useful. It'll be more clear on Monday why. But just know it stands in for a function when you don't want to give it a name, basically, or don't want to give it a whole new definition because it's just a one-off. You don't ever need to use it again. Yes?
So the cons and the X part is the
So no, this is the function part, right? So the accumulator, that starting value is nil here. So we start from the empty list and then map things onto it. And this actually I might have written this wrong because I think it actually also reverses the list.
so
Which,
that whole thing is the function.
yeah. So this whole piece is that A to B to B part. Yeah. Any more questions? Cool. Well, I had a question earlier. So what's the 30,000 foot view we're at? So I won't do any writing here yet. And I might come back to this again on Monday or on Tuesday next week as well to kind of tie it together again. But right now we're learning how to functional programming. It's this new way of programming. In some ways it's more intuitive, in other ways it's not. But it's a little bit more of a mathematical approach to programming, right? You can define these things. I could teach you how to write proofs on these. We don't offer that class yet. It's a shame because it's really cool stuff. And it's also a way of making sure your programs are always correct, which is really neat too. But it's a really nice kind of self-contained way of programming, right? You can build everything up from small building blocks. It's kind of the Lego approach to programming is the way I like to think about it. Now, why are we learning this in a programming languages class? Well, you might be thinking, okay, well, it's just a new kind of way of programming languages, you know, we're getting exposed to new stuff. Yeah, that's part of it. The other part is that this paradigm is super useful for designing languages. It's not just a new way of programming. It's actually pretty much what all of us PL theorists use daily, because it's a really, really good way of writing programs for programming, like designing new programming languages. We'll see this, I think on Thursday will be primary the lecture, what that looks like. But if we think about it a little bit, we almost defined a programming language already, if we think about it. So we defined the numbers. We defined a bunch of the operations on the numbers, right? We could think of that as a small little programming language, right? You couldn't write big expressions like with a whole bunch of pluses, and there aren't variables yet. So it's not quite a programming language. But you can see we're inching that direction, right? So that's where we're going. Starting next week, we're going to use this functional programming paradigm to then learn how we can define programming languages within that paradigm. And it'll all make a whole lot of sense and a whole lot of nonsense next week. So, or Thursday, I guess, is when I said we'd probably start that. So that's the 30,000 foot view. I'll probably revisit that on Tuesday again, because I do like to kind of go back and forth. But yeah, I think that's where I want to close things out today, a few minutes early. If you have questions, I'll hang out till 20 after. But otherwise, thanks for a good lecture today, guys. Thanks for hanging in there with technical difficulties, and I will see you all tomorrow.
Thinking about the extras at the end of the